Hello!
That's it. We started the meeting. Roger said that.
And it's been recorded.
Right, evening everybody.
Evening.
Evening.
Hey, welcome along. A year, can you believe it? Well, it's been all on the news today, hasn't it? So, yeah.
You're not wanting to sing happy birthday, are you, Dave?
Has John got his guitar out?
Just to say, Dave, it is my birthday tomorrow.
Oh, is it?
Oh.
Happy birthday for tomorrow, Raj.
Happy birthday. Yeah.
I'll be expecting some spare cake from Julian.
Yeah.
I've got mine here.
You will
What's
get any
that?
from me.
Spare cake? I don't think that exists, does it?
No,
in
it doesn't.
Julian's
It doesn't
case?
exist in his
No such
vocabulary.
Like
Not in
no
this
wine.
house. No.
Hi, Ron.
Hi, Michael from Dublin. Right, okay, I'll crack through because Jim's had quite a long day, so we'll get him cracking as soon as possible. Just about events, don't forget the Sky Diary is available on Team Up, so star-gazing.co.uk/diary. There's 3 calendars on there, you know. There's the events of stuff that's going on in the sky. There's space activities and events, so that any activities that I'm aware of, I put in there. And then space dates, which is any anniversaries and notable space things that are going on. Okay, so that's star-gazing.co.uk/diary. And you can download the Team Up app and carry it around with you. And any mistakes I'll correct, and it will correct automatically. So there you go. There are other meetings available, of course. Pete Williamson's Astro Radio Reach Out and Touch Space is on a Monday and Thursday evenings at 8 o'clock. I know a few of you take part in those. And then Stargazers Lounge have got the stargazing evenings on a Sunday at 7:30. So look out for those as well. Oh, thanks, Sean. Yeah. Try and keep us sane-ish. That's if we started sane in the first place.
Well, yeah. Absolutely.
Okay, so looking forward to the future meetings. I know most of you have seen these before. 6th of April, we've got John Thatcher's talking about the Webb Space Telescope. I saw John in the audience. Hi, John. And then 20th of April, we've got Mr. Cake Man himself. We're talking about crazy experimental spaceships. And then we've got Catherine Rayner Evans on the 4th of May talking about stamps and astronomy and space. And then 18th of May, still working on that one. 1st of June, Phil's going to talk about the history of the space shuttle. We've got some good anniversaries this year, haven't we, Phil?
We have, yes. The 40th anniversary of the first space shuttle flight, the 10th anniversary of its decommission, and the 60th anniversary of Yuri Gagarin's first flight. So lots going on there.
So
2 of those was on the same day.
Dave.
Hello?
Dave, so John Thatcher. It's a kind of tangential date, but there is a bit of a link. 12th of April is also the 84th anniversary of the first run of the Whittlejet.
Oh, right.
So 12th of April has got quite a few connotations. There appears to be some other thing people are excited about. Apparently hairdressers are open, but I think that kind of pales into insignificance.
Yeah, hairdressers.
Yeah, I need a trim now. And of course, we got the upcoming testing of the helicopter as well. Coming up.
Yeah, NASA just literally had a press conference on it. So they're saying around about the 8th of April is what they're saying.
Okay, so we'll have a look out for that, and if it's at a reasonable time, we'll have a watch like we did with the other events. That'll be good fun. Okay, and then 15th of June, we'll have the end of term party. So throw in your suggestions at what we ought to do for the end of term party. Okay, and then I'll have a rest for the summer, and then we'll come back probably late September. But you did say last meeting, yeah, we'll have a look out for the gastro pubs, and they'll pop up now and again when we feel we probably need one. Okay. Okay, so that brings me to tonight's meeting. I'm absolutely delighted that tonight, for our first anniversary, we've got Jim Al-Khalili, who's going to be talking all about the world according to physics. And I think that's a book. Yes. Oh, there's somebody waving it. Oh, Julian, yeah, waving it at us there. Excellent. So, Jim, if you'd like to share your screen, please, and tell us all about the world according to physics. So if everybody else
Absolutely.
can mute.
Absolutely, yeah. So do you need to stop your sharing? And
No, you should be able to
I can
just share over me now.
Okay. Who can start sharing? Where? Oh, I clicked it. It says advanced sharing options. Okay, yeah, fine. Here we go. Good. So, good evening, everyone, and pleasure to be, a privilege, in fact, to be giving your first anniversary talk. As Dave says, it's been a sort of bit of a hectic day for me today. I gave a talk this morning to the Institute of Physics. I did a webinar first thing, and then I had a few Zoom meetings, and then I recorded a Life Scientific. I don't know how many of you are Life Scientific listeners on Radio 4, but I recorded, obviously I'm not going to say who the guest was, but my goodness, the guest was nervous and kept, oh no, let me do that again. Oh, let me do, and so by 4:30, we had to end the recording. I think we've got enough for the program. Then I had a meeting with some guy on Zoom. You may know him. He's a famous astronomer, Brian Cox. That always goes down well when I talk to astronomers. We had some various things to do, and then a quick bite to eat, and then here. But this is obviously the highlight of my day. Obviously, it goes without saying. So I want to talk about, and trust me, this is not trying to flog my latest book, right? It's the book came out last year. In fact, it came out just before lockdown. I had in my diary, I was going to do a lecture tour of America, coast to coast. Everything this set up was published by Princeton University Press, based in New Jersey, and of course that obviously all got cancelled, as did a lot of the events in the UK. But I've been talking about the book online, and I've been giving these sorts of webinars, so it's been fun. I've written a number of popular science books, but this one was really sort of I say in the very first line in the book, this is my ode to physics, the subject that I fell in love with when I was a teenager. I mean, I didn't quite love physics as much as I loved Leeds United, but it was up there, it was getting close. And I've never looked back. I've spent my career whether as an academic, and I'm still sort of research active. I've got 5 PhD students, and I lecture to undergraduates at the University of Surrey, but also as a science communicator, writing and broadcasting and so on. And but it's all about really my love with this subject that still baffles me and that still throws up surprises. Now, there are lots of good books on physics and astronomy on the sort of popular science level. Some of them, absolutely excellent. And they sort of cover a lot of physics. A lot of them are like 1,000-page tomes that really get into a lot of detail about lots of stuff. I'd like to think of our knowledge of physical reality, or the physical universe, like an island. And as we learn more, the area of the island grows out into the ocean of the unknown, right? We don't know if that ocean goes on forever. We don't know if one day we will know everything there is to know about the universe. I doubt it. But my view is that there is an objective reality out there. The universe behaves in a certain way. And the job of physics, or even science in general, is to try and get as close as we can to that, to the nature of that absolute truth, that objective reality out there. But this book isn't an exploration of the whole island of our knowledge. This book is a walk around the shoreline. Okay, the very limits of what we know, the very limits of our understanding, and maybe wading out into the water a little bit to sort of explore some of the things that we still have yet to understand. I should say that when I first, when the book first came out, one of my colleagues at Surrey, who's head of physics at Surrey, Justin Reed, who's a word expert on dark matter, the nature of dark matter. So when I was writing about dark matter, I sort of sought his advice and feedback. And so when the book came out, I gave him a copy. And he was aware that in writing, I'd got a bit sort of polemical here and there, you know, sort of expressed my views strongly. So he said, well, if you put your thumb on the word physics, you get the world according to Al-Khalili, which might be more appropriate. Knowing me, I'm far too modest. Oh no, please don't. But and you can see it's a small book. So I just want to get across some of the basic ideas and you know, what is currently exciting me, what is currently at the forefront of some certain areas of fundamental physics. I'm not going to cover too much in the next 40 minutes or so. Back in 1981, Stephen Hawking wrote an article asking whether the end was in sight for theoretical physics. Because he wasn't talking about experimental physics or observational astronomy. He was talking about the theoretical physicist's search for a theory of everything. In fact, this first paragraph, he says, I want to discuss the possibility that the goal of theoretical physics might be achieved in the not too distant future, say by the end of the century, the 20th century. By this, I mean that we might have a complete, consistent, and unified theory of the physical interactions which would describe all possible observations. Basically, you know, what we would now say, you know, an equation you could wear on your T-shirt to describe all physical phenomena, all the forces of nature. It was thought then that we were getting close to discovering this theory of everything, you know, unifying the world of the very small as described by quantum mechanics and the world of the very large as described by Einstein's general theory of relativity. Well, Einstein, this was a few years even before what's now called the first superstring revolution. In the mid-80s, one of the candidates for such a theory of everything, still is one of the leading candidates, it was called superstring theory. The idea that the universe is made up of 10 dimensions, 9 of space and 1 of time, not 3 of space and 1 of time, but there are all these hidden dimensions curled up very small into tiny little balls, tiny little strings, much, much smaller than atoms. It's a powerful mathematical theory. I'll say something about it in a few minutes. But even before that, there were ideas as to where a theory of everything, or a theory of quantum gravity, as it's often known, may come from. But now here we are in 2021, 40 years later, and I would say that Stephen Hawking was wrong. We're not closer to a theory. We're not as close to a theory of everything now as many physicists thought they were 40 years ago. In fact, if you think back to the end of the 19th century, it was also thought then that we were coming close to the end of physics. You know, we had Newtonian mechanics, his law of gravitation, we had Maxwell's theory of electromagnetism and the nature of light, we had statistical mechanics and thermodynamics. What more was there that needed to be known? And then you hit that last decade of the 19th century and the discovery of the electron, the discovery of X-rays, radioactivity, heralding this revolution in physics at the turn of the 20th century with quantum theory and Einstein's relativity, which really then, you know, gave birth to what we still call a century later modern physics. So where we thought we were getting close to knowing everything about the physical universe, we realized we were wrong. Are we on the cusp of a similar revolution? I don't think so. I don't think quantum mechanics or Einstein's general theory of relativity are going to be overthrown, but there's a strong argument to say that one or both is incomplete, that there's still stuff we haven't understood, and we might not be able to squeeze it into our current theories. And that's what I want to say something more about. If we think about, you know, the end of the 19th century, there were these big discoveries that were made, experimental results that couldn't be explained. You know, have we had the equivalent in recent years? Well, here's 2 examples just from the last decade. We had the confirmation of the existence of the Higgs Boson in 2012 at the Large Hadron Collider. Made news all around the world, quite rightly so. And there's Sir Peter Higgs, whose name was adopted for this particle. He was one of a number of physicists who had predicted its existence many years earlier. Similarly, a few years later, in 2016, the first gravitational waves were detected in laboratories on Earth at the LIGO facilities in America. As I'm sure you will know, this picture here is not drawn to scale. Those two coalescing black holes are not in orbit around the Earth. In fact, that first observation of picking up these faint signals of waves of space itself came from the coalescing of two black holes over 1 billion light years away. So those gravitational waves, those ripples of space itself, have been traveling across the universe for over 1 billion years until they finally washed through Earth. It's a bit like dropping a stone in a pond and seeing the ripples on the surface of the water, but there it's the water that's vibrating, that's oscillating, that's waving, and those ripples move, the energy moves radially outwards. The same here, only it's not water that's waving, it's space itself. Again, a huge discovery, fanfare, Nobel Prizes all around, thank you very much. Since then, we've discovered more. But what I would say about both these discoveries is that neither was really a surprise. The Higgs boson had been predicted by Peter Higgs and others in the 1960s. So it was half a century earlier, they said this particle should exist if we're on the right tracks in describing the fundamental building blocks of matter. And sure enough, we find it. Gravitational waves, of course, were predicted by Einstein exactly 100 years before they were finally confirmed and detected. His general theory of relativity predicted that they should exist. What would have been more surprising is if they didn't exist. And the same with the Higgs boson. So in a sense, if I want to be cruel, both of these discoveries, important though they were box-ticking exercises. Okay, we know the Higgs boson should exist. Yep, we found it. Where's the gravitational waves? Finally, yep, we found it. It's not to detract from the incredible achievements of experimental science and engineering that made these observations possible, but what they told us about the universe wasn't something new or unexpected. The only real unexpected discovery, truly surprising discovery, certainly in my lifetime as a professional scientist, took place in 1998. And that, of course, was the discovery in astronomy that distant galaxies at the edges of the visible universe are receding at a speed that didn't tally with what we expected. We have known that the universe, that space is expanding ever since the measurements of Edwin Hubble at the Mount Wilson Observatory in California in the late 1920s. He looked at distant galaxies and saw that the light from them was redshifted, was stretched towards the red end of the spectrum, suggesting they were receding from us. And the further away the galaxy was, the faster it was receding. That was something that fitted in well with Einstein's theory of relativity, suggesting that the universe began from a hot, dense state, the Big Bang, and was expanding, has been expanding ever since. And for non-scientists, it's quite a difficult concept because people imagine the Big Bang to be an explosion in space. It's not. It's a stretching of space itself. The matter stays where it is in essence, but the space itself stretches, and that's still taking place today. And until 1998, the understanding was that expansion should be slowing down. The gravity's putting the brakes on the expansion. And yet, in 1998, and this is my cartoon for it, I wrote a Ladybird book. You remember Ladybird books? These are non-fiction Ladybird books. You have text on one page and illustration on the other. Well, they revived them. Penguin books have revived them. And I wrote the Ladybird book on gravity. And I work closely with an artist, Jeff Cummins, and he produced these lovely pictures. So I use them. He's given me permission to use them. And this is the way I describe this mysterious force, because what it's doing is making the expansion of the universe not slow down, but speed up. What astronomers saw when they look at distant galaxies was that they were expanding more slowly than they should have been, given how far away they are. If you put two dots on a rubber band and you stretch it, those dots don't move along the rubber band. They stay where they are, but the rubber in between them stretches. That's what the expansion of space means. But if those dots are further apart, then there's more rubber between them to stretch. And so they separate more quickly. So that's what we mean by things that are further away, expanding, moving away from us more quickly. Now, because we're seeing these galaxies that are very, very far away, what we're looking at is what they were like a long time ago, because it's taken a lot of time for their light to reach us. So when we observe these distant galaxies, we're observing the universe when it was much younger. And what we see is, rather than the expansion being much quicker in the past and now it's slowing down, the expansion was slower, it's actually faster now. So space is stretching more quickly. This dark energy, which is, we've given it a name, which is, something, is still a mystery. We still don't quite understand its origin. A lot of physicists will say, well, we're almost confident that it's something called the quantum vacuum energy, but again, that's just another name. The fact that we can't explain it with confidence suggests that there's still more that we need to understand. So that's a very nice example of something that's out there in the ocean of the unknown that we're still trying to understand. But why are we obsessed with trying to unify all our understandings of physics? Why are we obsessed with trying to find a theory of everything? So on this slide, I'm very proud of this slide, I have to say, because on PowerPoint it took me a long time when I put it together to get all the animations right, to reveal hidden words, what a colleague of mine once called intellectual striptease, slowly revealing the words. So what I want to talk about is, in one slide, our journey of unifying different ideas, different phenomena in physics, because that sort of gives a rationale for why there is still this obsession to look for a theory of everything, a theory of quantum gravity. Well, the earliest, in modern science anyway, the earliest unifying idea is, of course, Isaac Newton's realization that the apple falling from the tree, being pulled down towards the ground, is succumbing to the same universal force that keeps the orbits of the planets in orbit around the sun and the moon in orbit around the Earth. And with that, Newton comes up with his law of gravitation. I should say that you can see the fonts are small here, so gives you an idea. I'm going to fill this up with words. Nor am I going to spend too long explaining every step of this unification journey. So that's Newtonian gravity in the 17th century. We then jump a couple of centuries later, and the mid-19th century, built on work of Michael Faraday, the Scottish physicist James Clerk Maxwell unifies electricity and magnetism. He shows that they are both part of the same single force, the force of electromagnetism. And at the same time, he shows that light itself is an electromagnetic wave, oscillating electric and magnetic fields traveling through space. So again, like falling apples and orbits of planets, until Newton came along, why would you think that they had anything to do with each other? You've got this mysterious thing that causes objects to want to move down towards the Earth, and then you've got the laws of nature that govern the motion of heavenly bodies. It wasn't at all obvious that they should be the one and the same force, and to a lesser extent, I guess, it wasn't obvious that electricity and magnetism were part of one and the same phenomenon. Jump down again in the mid to late 19th century, and you got ideas about heat and energy built on work of people like Carnot and then later Ludwig Boltzmann, unifying those ideas about energy and work, you know, temperature and pressure and so on, linking them with this new field called statistical mechanics, gave rise to what we would now call thermodynamics. Thermodynamics is, and I describe this in the book, as one of the 3 big pillars of physics to this day. Okay, where do we jump to next? Okay, no surprises here. Space and time. Again, no one would have anticipated that these would be unified into a single entity, 4-dimensional space-time, but that's what Einstein did in 1905 in developing his special theory of relativity. I'm now going to speed up so I don't run out of time telling you other things, but let's see what else I can do to unify stuff. Well, Einstein, 10 years after his special theory, he comes up with his general theory where he describes Newtonian gravity in a new way. He says Newton was wrong about gravity being this invisible force, this invisible rubber band that pulls masses together. No, it's the shape of space-time. Objects, masses, bodies embedded within space-time cause it to curve around them. And that manifests itself. We sense that curvature as a force, and we think of it as an invisible attractive force we call the force of gravity, but it's really the shape of space-time. General relativity gives rise to modern cosmology. And of course, modern cosmology then tells us so much about the structure of the universe, from predicting the Big Bang to the deaths of stars becoming black holes, to the structure of galaxies, and all sorts of other observations on the grander scale. They all really follow on from general relativity, including what I mentioned earlier, the idea of gravitational waves, ripples through space. Okay, where to jump to next? Okay, down here, turn of the 20th century, probably quite surprising, but physicists and chemists were still arguing about whether atoms were real or whether space was infinitely divisible, continuous. Well, by the beginning of the 20th century, people like Einstein had predicted by explaining Brownian motion that atoms are real. People like Ernest Rutherford is the first to understand what the inside of an atom looks like through famous experiments with Geiger and Marsden, showing that most of the atom's empty space. There's a tiny nucleus in the middle with electrons buzzing around the outside. And there are new forces inside the atom, inside its nucleus. Until then, there were only 2 forces, fundamental forces that were known: the electromagnetic force and gravity. Now we have these forces that provide the glue that hold nuclei together. Well, similarly, in the 20th century, beginning of the 20th century, we have quantum theory. In order to explain a number of experimental results, people like Max Planck and Einstein developed early quantum theory, a theory that describes the subatomic world. And by the mid-1920s, that has become the full quantum mechanics, which is different from Newtonian mechanics. That all the stuff, the physics we learn at school, momentum and kinetic energy and the trajectories of particles and swinging pendulums and bouncing balls, all of that is Newtonian mechanics. Get down to the subatomic world, you need a new kind of mechanics, quantum mechanics. And famously, it's counterintuitive, it's mysterious, particles being in 2 places at once, being able to tunnel through energy barriers, two separated particles instantaneously in communication, all that stuff. Well, quantum mechanics now becomes, say, the mathematical model that describes reality at the tiniest scales. Very soon after its development, it's unified with Einstein's special theory to give us what's called quantum field theory. Quantum field theory is then used to describe electromagnetism, and we come up with what's called quantum electrodynamics. The 2 forces inside the nucleus, We have the weak nuclear force and the strong nuclear force. They are also described by quantum mechanics. And a quantum field theory is discovered to describe them. So the strong nuclear force is described by a quantum field theory called quantum chromodynamics. The weak force is combined with quantum electrodynamics to give the electroweak theory. That plus quantum chromodynamics gives us the standard model of particle physics. So you can see all these disparate, originally thought to be independent phenomena and laws of physics are connected. And gradually you'd think it's getting simpler, right? We now have the standard model of particle physics to describe the world of the very small. Similarly, cosmology gives us what we call the standard model of cosmology. So what you've got here, lambda CDM, lambda, Greek letter lambda stands for what's called the cosmological constant. Essentially, what many physicists believe is the mathematical way of describing dark energy, but we're not sure. CDM stands for cold dark matter. Now, dark matter, again, is another one of those mysteries out in the ocean of the unknown, because we don't know what it's made of. We know it's there. It has nothing to do with dark energy. The fact that they both have the word dark in front of them doesn't mean they're connected. Dark matter and dark energy. It's just, they're both stupid names, right? We shouldn't have called either of them by their names. Dark energy could have been called a quantum vacuum or something like that. Dark matter would be much better if we called it transparent matter or invisible matter. It's not dark. But anyway, we have dark matter and dark energy, and we don't quite understand them. So somehow they have to feed in to the standard model of cosmology, and we're not quite sure what that would look like. But the point is that what Stephen Hawking was alluding to in 1981 was a combination, a bringing together of the standard model of cosmology, everything we know about on the cosmic scale, and the standard model of particle physics, everything we know about the micro scale, into a theory of quantum gravity. Because essentially you can think of it as the quantum bit is the standard model of particle physics, the gravity bit is the standard model of cosmology, and it's bringing them together. And it's not been an easy task, and we still don't quite know how to do it. My personal view is that we are not going to be able to get to a theory of everything unless we bring in this third pillar of physics, namely thermodynamics. Okay, and I'll allude towards the end of the talk why that is important. But there's still lots more we have to do. I'd realized when I made this slide, I still had some white spaces, so yeah, I had to fill them. So of course, quantum mechanics leads to this new, a whole very vibrant new area of research called quantum information theory, which may provide some inklings towards how we get to a theory of quantum gravity. We have other areas such as complexity theory, non-equilibrium statistical mechanics, non-equilibrium thermodynamics. There's something called the black hole information paradox, which Stephen Hawking, before he died, was very interested in. Some people have argued that whether or not that has now been solved, I don't believe it has. Lots of question marks, lots of things in fundamental physics that people are still thinking about that I think need to be resolved before we get to a theory of quantum gravity. And where are the next surprises going to come from? Well, first thing this morning when I got up and I was checking the BBC News website, I don't know if any of you saw it, but there was this news that there might be the suggestion of a new particle detected at the Large Hadron Collider. So this is an article by the BBC science correspondent Pallab Ghosh, where he says in the data at the LHC, they've discovered hints of a new type of particle called a lepto quark. I think something like that. Anyway, the idea that certain particles, when they decay, when they're short-lived, in this case, one of the heavier quarks, when it decays, they know how it should decay. And if it doesn't decay in that way, then there may be a new force, a new particle that is has yet to be detected that may be behind it. So there may be hints that the standard model, if not broken, is certainly incomplete, and we sort of need to watch this space. Certainly, we're not close to being able to resolve things. Well, when it comes to theories of everything, I mean, there are still many physicists who are working towards it, and certainly if they are working on their pet theory, they would argue that they're on the right tracks. Their theory is the one. It becomes almost like a religion. You know, I'm right, my theory is right, and everyone else is an idiot. The two leading contenders, depicted here by two superheroes having an arm wrestle. So on the one hand, you've got string theory, and there's a big community of physicists around the world that has been, for decades now, working on this idea, string theory, 10-dimensional space-time, unifying the four forces of nature. A lot of time and effort and talent has been invested into string theory, but it hasn't made the advances and progress that I think a lot of people had been hoping for. It's very powerful, very elegant mathematics. In fact, the mathematics has proven to be very useful in other areas of physics. It's been picked up by condensed matter physicists, for example. But elegant maths doesn't mean that is the way nature behaves. It doesn't mean that is that physical reality is down to 10-dimensional strings. On the other side, you've got, in a sense, a rival camp working on what's called loop quantum gravity. So whereas string theory tries to unify the four forces of nature and that tries to bring gravity into the fold, into quantum mechanics, giving it a quantum description, and even there's even a particle, the graviton, that's suggested to exist. Loop quantum gravity starts from the other end. It starts from space-time and says, let's try and quantize space-time, discretize space-time. So it's a bit like looking at a picture, and if you magnify and magnify and magnify, you get all the way down to individual pixels. Well, the idea is that even space and time themselves, if you zoom down to a tiny enough length and time scale, they become grainy, they become fuzzy and pixelated. We don't know if either of these theories is the correct description of reality. In fact, there are physicists who argue that they're not even proper scientific theories because they're not testable yet, and therefore they're not falsifiable. We don't know how to design an experiment that would test whether or not one or other of these was right. One of them may be, but maybe they're both wrong. Maybe we have to go back to the drawing board and start again. Just to give you an idea of even fundamental ideas like space and time themselves, we're still struggling with them. If I just ask a simple question, what is space? People like Aristotle, great Greek philosopher, and then much later Descartes, both believed that space didn't have an independent reality without matter, without the stuff that's in it. Space is simply the gap between matter, between objects, between 2 points. For example, if you have imagine a box that's completely empty. There's a vacuum inside it. And I know down in the quantum world, you can never have a vacuum because particles are popping in and out of existence all the time. But let's ignore that for now. Imagine a completely empty box. What happens if I take the walls of the box away? Does the space that was inside the box still exist? Or did it only exist because there were walls to the box? What if that box were inside a larger volume of empty space, defined by the walls of a larger cube? Then I take away the walls of the smaller box. Does the space that exists inside it now still exist because it's part of the larger volume? I mean, these are indeed sort of philosophical questions, but they were argued by physicists. Newton, for example, believed that space was a real thing. It had to exist. It had to pre-exist. You had to have space in order to put stuff in it. Okay, you need space, you need time, and then you can have matter inside it, and you can have matter moving and events taking place. So who's right, Aristotle and Descartes or Newton? Well, today we would go by what Einstein tells us the nature of space is. In 1916, so very, very shortly after he had published his general theory of relativity, he wrote a book, essentially a popular science book. This was not a textbook, called Relativity, the Special and General Theory. It was published in German, and then it was translated into other languages, including English. And I have a copy on my shelf. Unlike many other books, when it went through new editions, none of the main text in the book was changed. But Einstein added appendices to the book, and the most famous one appeared just 1 year before he died, Appendix 5 in 1954. And in that appendix, those few pages are some of the most profound words ever written down, or conceived of, I guess, by the human mind. So, for example, Einstein says, if we imagine the gravitational field to be removed, and by gravitational field, of course, he means matter and energy, because with matter and energy, you have a gravitational field. If you imagine the gravitational field to be removed, there does not remain any space-time, but absolutely nothing. So you can see he's sort of siding with Aristotle here. Without matter and energy, and therefore a gravitational field, there is no space-time. But he also then says space-time does not claim existence on its own, but only as a structural quality of the gravitational field. So he's saying space-time is a quality of the gravitational field. The gravitational field and space-time are one and the same thing. So space-time is a real thing. So here he's siding with Newton. In fact, space-time, even more than Newton, space-time is something that can be, it's the fabric of the universe. It can be stretched and squeezed and bent and curved. And if you think about Einstein's theory of relativity, you realize why he says these things. His general theory is basically described by an equation called the field equation. I won't show it to you, but basically it's an equation. It's got an equal sign, right? As equations tend to have. On one side of the equal sign is space-time, and on the other side is matter and energy. So you can see you can't have one without the other. If matter and energy become zero, then space-time disappears. Likewise, space-time zero, matter and energy disappear, because space-time is the gravitational field. So if there's no gravitational field, there can't be any matter or energy. So such simple, profound pictures of the nature of space are still things, that we might be struggling with. Even more in your face sort of, concept that shows how we still have a way to go, not quantum mechanics, I won't go into quantum mechanics here, is what is time? Yes, there's the usual, what is time? Well, it's the universe's way of stopping everything from happening all at once, right? Or how fast does time go by at the rate of 1 second per second, all that nonsense. But then the nature of time is something, physicists, philosophers, theologians have struggled with, for millennia. But what's interesting is if we look at, these three pillars of physics, relativity, quantum mechanics, and thermodynamics, they each give different definitions of what time is. So general relativity says time is part of the fabric of the universe. It's a dimension. It's the fourth dimension. It can be stretched and warped by gravity. The gravitational field is the structure of space-time, but time is just a direction, an axis. It's just, and you can have past, present, and future all coexisting all at once on this time axis. Quantum mechanics says no, time isn't a dimension. It's a number. It's a parameter. In the equations of quantum mechanics, like Schrodinger's equation, you plug in a number, you have t, you plug in a value for t, which tells you the state of the quantum system you're describing at that moment in time. like, you know, what an electron is doing in a box. You solve the equation, you know, dynamically, you evolve it in time, and you can work out what that quantum state is at some other later time, T2. So, you know, for a given time, you put in a number and that tells you what the state of the system is at that moment. You could crank the handle backwards and work out what the state of the system was in the past, because in quantum mechanics, time is reversible. Okay, things backwards, forwards, it doesn't matter. There's no direction to time. So you have time as a dimension, time as a number. And then you have thermodynamics, which says, no, time is an arrow. It points specifically, irreversibly from past to future, according to the famous second law of thermodynamics. You know, balls roll down hills, milk stirs into your coffee, it doesn't unstir. We grow older, stuff runs out, becomes more untidy, things get more mixed, right? All that stuff that we understand that differentiates the past from the future is down to thermodynamics and the arrow of time. My view is that we are not going to get to a theory of everything unless we unify these three concepts. And just the fact that we still have three definitions of the nature of time should tell us that we're still some way away. In fact, my current research interest, I mean, so my research area started off as a nuclear physicist. So I was modeling nuclear reactions in theoretical nuclear physics. So basically quantum mechanics. But then in recent years, I started looking at applying quantum mechanics in other areas. In particular, an interest of mine is looking at quantum effects in biology. Certain quantum phenomena taking place inside living cells. So there's a whole new field called quantum biology, which is very, very, very exciting at the moment. But also, my interest has moved to how to combine quantum mechanics with thermodynamics. Now, there is a field of science called quantum thermodynamics, but giving it a name doesn't mean all the questions within that field have been answered. The point that, you know, the area that I've been thinking about in recent years is, how does irreversibility emerge out of quantum mechanics? We sort of know that, you know, I mentioned quantum phenomena can move backwards and forwards in time, but when you make a measurement, when you observe it, or rather when the system interacts with its surroundings, then irreversibility kicks in, and it gains an arrow. So how thermodynamics and quantum mechanics merge together is something that will help us certainly understand the nature of time. Similarly, you know, people trying to unify thermodynamics with relativity theory. What I mentioned earlier, the so-called black hole information paradox, that's precisely to do with how lots of concepts in physics, thermodynamics, the nature of information, the gravitational fields around a black hole, how they all combine. So all these areas are really, you know, there are still big questions. When we talk about what is there that's yet to be understood, usually what people say is, well, you know, we don't know the nature of dark matter or dark energy, or we don't know if there are supersymmetric particles, or is the standard model true or not? But actually, the honest answer is we don't even know the nature of time itself. Its irreversibility, how it is brought together within these three different pillars of physics. One thing I did want to end on is that, you know, people say, well, if you theory of everything, maybe you have to change quantum mechanics, you know, or maybe general relativity has to be tweaked, or maybe both are wrong and we have to come up with something else. Bring in thermodynamics. Something has to give. Maybe more than one thing has to give. Well, so the last thing I want to say is, here's a quote from Einstein, who says, thermodynamics is the only physical theory of universal content which I am convinced will never be overthrown. Here's the guy who gave us general relativity, and yet he's prepared to say that his theory of general relativity, beautiful though it is, may have to change, may be overthrown. Quantum mechanics may be overthrown. And Einstein, he had his issues with quantum mechanics, of course, believing it to be incomplete. But he thinks that thermodynamics, that third pillar, is the one that will survive intact if other things have to go. So it's interesting to think that we still have, here we are entering the third decade of the 21st century. We aren't closer to a theory of everything. We aren't, and certainly not as close as Stephen Hawking thought we were 40 years ago. But we're starting to realize we may have to go back, not back to the drawing board, because we don't think quantum mechanics is wrong or general relativity is wrong, but they may be incomplete. There may be a bigger hidden reality out there that is yet to be discovered. Now, maybe this discovery of this particle at Large Hadron Collider is you know, a week or 2 weeks or a year or 2 years from now, we'll turn back and say, oh yeah, that was the moment when physics was revolutionized. I doubt it, but for me, what is the joy of doing the research that I do is that wading out into the water, rolling up your trouser legs and wading out into that ocean of the unknown, looking at those mysteries, trying to discover how they fit in with our understanding of the universe. And we're a long way, I think, from reaching the further shores. Does that ocean of the unknown go on forever, or will we one day know everything? Who knows? But there's a long way to go yet. And I think I will stop talking there. So thank you very much.
Brilliant. Thank you very much, Jim. Absolutely amazing. It's always incredible when you hear a talk like that, how much we have learned, but also how much we still don't understand. And of course, the more we learn, the more questions that get raised.
Yeah, absolutely.
And talking of questions, we'll see if we can, if people want to. Have you got time for questions now, Jim?
Yeah, absolutely. I'm happy to take some questions, about 15 minutes.
April had a question. So April, would you like to unmute yourself and ask your question?
Yeah, this just simply, it's about the rubber band. And Jim explained the universe expanding according to having two dots on a rubber band, which I found really interesting. And then it got me thinking about universes that were expanding or stretching away from us. So how close then are we to the center of the universe, or close to where the Big Bang was? Because I was given the impression that it was 13.8 billion years away. But then if all the universes around us are stretching away at the same time, maybe we're closer to the middle than we thought.
Right. Okay. So that's a very, very good question, April. It's a really a common question. It's one of those questions which takes a while to get your head around, but I don't know if I'm going to satisfy you with my answer, but I'll try. Basically, the Big Bang, we don't say so. The Big Bang happened 13.8 billion light years away. It happened 13.8 billion years ago, but it's not that we are in a privileged position. The Big Bang happened everywhere, because everywhere was all in the same place. Imagine that rubber band could shrink. You know, normally a rubber band, if you leave it alone, right, it has a certain length, right? But imagine a rubber band that had zero length. So all the dots, you could put lots and lots of dots on it, but all those dots were all scratched up in the same place. That's the Big Bang. So you don't say, where did the Big Bang happen? The Big Bang happened everywhere. The Big Bang, what the Big Bang was all the dots being together, stretch them, they all move apart. And in fact, probably pulling a rubber band isn't the best analogy, but maybe blowing up a balloon with dots on the balloon, right? And the universe is the surface of the balloon. There's no inside of the balloon. That's another confusion. So what's inside it? Well, nothing. But the whole surface of the balloon at the Big Bang was a tiny dot. So everything was together, and then everything moved apart from everything else.
Actually, that helped a lot. Thank you very much.
Good. I'm so relieved when I see people nodding. That really gives me a lot of pleasure. So yes, pennies are dropping.
Gordon, you were next, I think.
Yeah, thanks, Jim. Fantastic talk. Thank you very much. Really, really interesting.
Thank you.
When we take a look at the laws of thermodynamics, and we know that there's a arrow of time, and we observe that also at a cosmological scale, where we're kind of heading towards the death of the universe. Yeah. Doesn't that just kind of make time as a value within quantum mechanics just maybe a mathematical construct, and not really necessarily related to the overall nature of time itself?
Well, all the time we're looking at these different scales, and if we look at, I mean, the heat death of the universe and the expansion of the universe is essentially following, as you say, following thermodynamics. We must have somehow started from a very special low entropy, highly ordered state at the beginning of the universe, and entropy has been increasing until the heat death, when entropy is a maximum. But if we want to combine quantum mechanics with general relativity and thermodynamics, then they should all be operating on the same scale. Now, whether you play by the rules of general relativity or the larger scale or the smaller scale, the idea is that that unified picture should also include that arrow of time within thermodynamics as well, and within quantum mechanics as well. And we know space-time has to be quantized, because if an electron is in a superposition of being in two places at once, then that electron is causing some curvature of space-time around it, albeit very small. But the curvature of space-time is also in a superposition of being curved in two places at once. So we know that quantum mechanics has to describe space-time. So probably down at those smaller scales, the nature of time, or the irreversibility of time due to thermodynamics, has to also emerge or be combined naturally with quantum mechanics. And at the moment, it doesn't. Some people talk about this as the so-called measurement problem in quantum mechanics. How do you go from unitary evolution, the Schrödinger equation, to something that is irreversible in time, namely what happens to the system when you collapse the wave function or make a measurement? But it's still hand-wavy. So it's still that consistent picture about the arrow of time from thermodynamics. We don't yet know how to incorporate it into quantum mechanics.
Okay, so we're definitely missing something within quantum
mechanics. I believe we're missing something. I believe we're missing something. Maybe there are others who disagree with me, but I think there's something yet to be understood. I hope so anyway, because that makes life more interesting.
Thank you very much.
There's loads of questions coming in the chat, Jim, but I think Colin was next.
I will keep my answers as short as I can to get as many of you through.
Okay, Colin.
Thank you, Dave. Thank you. Great talk, Jim. Loved it.
Thank you.
I've got every word. It's a pleasure to listen to you. My question is, are we sufficiently intellectually advanced enough to understand physics to be able to unify a theory of everything? Or should they, or are they, living side by side, symbiotically interacting when physics demands it?
That's a good point. We may have reached the limit of what our sort of dumb ape brains can cope with in terms of, it may be that it is too complex. I mean, this idea that, I think the journey to unification might give the impression that things were complicated and messy, and it's now ordered and simplified, and we've only got one or two sort of concepts because it's so unified. But it also could be the case that things are just too complex to understand. In fact, it's even being suggested that we may have to rely on artificial intelligence to find the theory of everything. So an AI might be the next Einstein, because AIs are now reaching a level of sophistication that they are able to see patterns in the data, patterns within them, maybe within the mathematics, that is just beyond our brains. So maybe we'll never get to a theory of everything because it's too difficult. Maybe we're going to need some help from artificial intelligence. But that's fine by me. I don't care.
As long as we get there.
Yeah, exactly.
Thank you.
Brilliant. Anybody else? You got another question, John? You got your hand up still, or?
Yeah. You're joining me, aren't you, Dave? I hope. I'd like to ask Jim two questions, two totally different questions. One is, you say the repeated phrase, gravity is just curved space-time. So are people still looking for gravitons, And isn't that a waste of time? And secondly, completely different, on the life scientific, which I thoroughly enjoy, have you attempted to get Professor Gillian Wright at the Royal Observatory, Edinburgh, onto your programme? Because she is the principal investigator for the mid-infrared instrument on the James Webb Space Telescope, which should launch on 31st of October. She's a very private person. I know her very well. But if you haven't got her on, why haven't you got her on?
Okay, right. Well, to answer your first question, I think looking for gravitons experimentally is indeed a waste of time. We've only just detected gravitational waves. Finding gravitons is so many orders of magnitude beyond anything that our instruments would ever be able to see at the moment. Forget it. But that doesn't mean that we shouldn't be postulating the existence of such particles as is predicted, for example, in string theory. I'm agnostic about whether string theory is the right way to go. I don't work in the field, nor do I work in a rival field which will, slag it off. So I don't know whether gravitons exist or not. But I think experimentally, no. We shouldn't even be thinking about finding a way of detecting them unless there's some indirect sorts of experiments that we haven't been clever enough to come up with yet. No, in terms of the guest you suggest for Life Science, we haven't had her on. What might be a good idea, and I say this to people, send me an email if you think there's a guest.
Yeah, I have done.
You have done. then I would.
But I got no reply.
Oh, send it again. Send it again, because what I tend to do when I get suggestions for guests, I often just pass them on to my series producer at the BBC. We have a pool of potential guests. And so sometimes we have an idea, this person will be really great, but they don't appear until the following year, because we, in every run of 8 of the Life Scientific, we try and spread it across different areas of science. We spread it across male, female, 50%, and so on. So, but if a guest is worthy, we'll get to them.
Could I just say, it's very difficult to try and track down an email address to send to you in the first place, but I found something eventually. But the point is, the UK led 50% of the mid-infrared instrument. The UK led a 10-nation, 32 scientific institute consortium in partnership with the Jet Propulsion Lab, and Gillian Wright was the principal investigator. She's the lead person. She's a fantastic example for science, astronomy, and women, and she's a very canny operator. She's both a brilliant scientist, astronomer, and she understands how politics work, and boy, is she clever. But she's a very private person. She may not want to go on, but can I send something through Dave Eagle to get to?
Send it through David. Yes, send it to my University of Surrey email address. That's the main one that I use. Al-Khalili at Surrey. If you go to my name and University of Surrey, there's my contact.
I think that's where I sent the email.
Then I should have got it. As you can imagine, I get a lot of emails. I try and deal with what I can. But no, she sounds like an ideal guest for the Life Scientific, to be honest.
Persuaded to come on.
Well, that's the other thing. Sometimes it's fascinating scientists who've done something remarkable in their lives, but also they need to come across engaging on radio, and so some I think a few, there aren't many that we've said would come on and then they say no, I don't want to. I think only two guests in the last 10 years have turned us down. One was Stephen Hawking and the other was Tim Berners-Lee. Stephen Hawking, I can understand why, because to have to pre-record questions and answers there'd be no point on radio anyway. Tim Berners-Lee, well, we might ask him again. We'll see. But people will come on if, hopefully, if invited, and if she's keen, then we'd approach her. Absolutely.
Yeah. Thank you very much indeed.
You got time for one more question, Jim? Because
go for it.
Got his hand up over there, and then we'll let you get away. You've had a long day.
Thank you,
Ron.
All right. Sorry, I didn't hear. Hi. My thought was, most step changes in science in the past have been driven either by a move forward in our ability to measure and quality of instrumentation, or through developments in mathematics. What do you think is going to be the next driver of change?
It's difficult to know, because a lot of the theories that are being talked about now, you know, whether it's to do with the nature of multiverses or quantum gravity or so on, are so far removed from what we can measure observationally or what experiments we can design that it's difficult to know. But I do think the breakthrough will have to come from experimental science. An observation of a dark matter particle, whether captured from space or whether created at an accelerator, or some clever result from condensed matter physics. I think there's no shortage of speculative theoretical ideas, but we're waiting to be able to test them. So I think the next big breakthrough, in the same way as, you know, dark energy in 1998, a century earlier, X-rays, radioactivity, the electron, the big breakthroughs come from, you know, from experimental science. You do have the revolutions in theoretical physics, but they tend to be as a result of trying to explain an experimental result. Right, so Einstein's special theory of relativity was to explain the Michelson-Morley experiments about the nature of the ether. Quantum mechanics and quantum theory was to explain various results experimentally that didn't make sense in classical physics. So even the theoretical advances tend to be off the back of trying to explain an experiment. A theory without any experimental testing that's possible remains, in my view, pretty maths. We need empirical science to, I think, show us the way, whether it's observations or laboratory experiments.
Thank you.
Brilliant. Well, thanks very much, Jim. That's been absolutely fascinating. My
pleasure.
Blowing, and yeah, all sorts. Sorry we didn't get a chance to answer all the other questions, and yet Leeds United didn't get mentioned too much.
No.
During the evening. Okay, is it okay if I copy the questions and send them to you?
Yes, please do.
And
Yeah,
I can pop them on the website. So if anybody's asked a question in the text, I'll send them to Jim and see if we'll get the answer.
I'll try and get answers back to you. Absolutely, my pleasure.
Brilliant. Thank you very much, Jim.
Okay. Well, thank you, everyone.
Okay. Thank you, Jim.
Pleasure
Thanks
to
for
be with
giving
you.
your precious time. Great talk. Beautiful.
Thanks ever so much.
Beautiful.
Cheers,
Thank
then.
you very much.
Bye bye.
Thank you.
Bye.
Thank you, Jim.
Thank you.
Whoa.
Thank you. Bye.
That was good. That was a good way to end the year, wasn't it?
Fantastic.
Brilliant. Well done, Dave.
Super stuff. Thank you.
Very good.
Oh,
That was our biggest event of the year. That was, David.
We had up to 90 people at one point, didn't we?
Yeah, over 90.
Wow.
Right on.
God.
Please, quick.
Oh, fuck. Oh, dear.
Good stuff. Okay then, right.
But hey, Dave.
Yep.
When we have like the second anniversary, who are you gonna get on?
Oh, send me some ideas. Well, Julian would be really famous by then.
For eating cake.
Where's the cake?
You can play
The cake theory of everything.
Yeah. Excellent. Right, well, everybody, thanks very much for all coming tonight. It's been a year. What a year it's been. Let's hope the next year starts to get a bit easier as we go. Okay.
Thanks, Dave.
Thanks so much, Dave. Thanks for everything.
Look after yourselves, and of course, I'm going to say, keep safe, keep well,
Keep looking
up. Take care,
everybody.
folks. Bye.
Bye.
Bye.